Okay, thank you very much for the invitation to come to this conference. I'm very happy to be here. And I'm going to be telling you about some work that I did with my student Thomas Reis, trying to apply the techniques of resurgence to physical systems, superconductors. So what is the motivation for this? Well, as you have seen in the talks today, precision resurgence, I mean using resurgence really in its full glory, has been applied very much into quantum mechanics, matrix models, and so on. But these are, in a sense, toy models, especially now that we have an engagement with the European taxpayers with our ERC grant. We should try to move to something a little bit more serious. And more Yeah, I know. But records can be destroyed, as you know very well. And also, more from the point of view of mathematics, I think it's very interesting to find new sources for transities. And I think I will try to present you here a really very concrete source for transities. Now, one possibility if you want to enlarge the examples where resurgence can be applied is to look at quantum many-body systems in low dimensions. Because I think they offer a very good balance between analytic control and physical relevance. And sometimes they are simpler than quantum field theories. We have seen the talk by Mittat, where he has been already addressing issues of resurgence in quantum field theories. But in a sense, many quantum many-body systems are even simpler than quantum field theories, although they share the same flavor of quantum field theories. Now, there is a more concrete motivation, and it's the following. Now, in resurgence, we search for non-perturbative effects. So we really want to correct perturbative expansions with exponentially small effects in coupling constants. But actually, one of the most important non-perturbative effects in quantum physics, and one effect which is actually something that people have measured, etc., is the superconducting energy gap. And this is a robust, I will explain you a little bit more what it is. I understand that most of the audience here is not an expert in quantum many-body theory, neither am I, by the way, so this is also a disclaimer, I'm not an expert in quantum many-body theory, so I'm going to tell you what is the superconducting energy gap. But this is a non-perturbative effect in quantum physics, exponentially small the coupling constant, and is a robust feature of Fermi monibody systems with an attractive interaction. You have a weakly coupled Fermi system with an attractive interaction, there will be a superconducting energy gap. And this effect feature very importantly in the famous paper by Bardeen, Cooper, and Schrieffer in 1957, where the modern theory of standard superconductors was built. Now, once you see a non-perturbative effect, something which is exponentially small in the coupling constant, and if you are doing resurgence, a natural question is, can you incorporate this effect in some way or another in the theory of resurgence? Is, for example, to make the question more concrete, can you relate this exponentially small effect, for example, to the large Torre behavior of the perturbative series? So this is the kind of question that I want to explore in this talk. So let me then make a short summary what is the superconducting energy gap. So imagine I have a system of spin-half fermions, which have the standard non-relativistic kinetic term, and then you have like a interaction. Now this is a two-body interaction, so I'm using the language of quantum field theory to describe this Fermi system. So this is a two-body interaction, and for simplicity, this is a delta function interaction. Okay, in one dimension, the delta function interaction actually is very well behaved. In two dimensions, higher dimensions, you have to do a little bit of work, but you can also consider it. And for simplicity, I will consider this kind of system. So you have a coupling constant here, G, M is the mass of the fermions, sigma is the spin of the fermions, and so on. So this is a system of weakly interacting fermions which interact with this delta function interaction. And imagine that you want just to compute the energy of the ground state of this system of fermions. Now, of course, this is a basic question in quantum many-body theory, and you can answer these questions with Feynman diagrams. Now, you have to use the Feynman diagrams of many-body theory. The energy, ground state energy of this system is going to be the energy of a system of free fermions, and then you will start adding corrections a la Feynman. So the first correction is what is called the Hartree term, then you have the Fock term, and you have more complicated diagrams, and you have an infinite series of diagrams.
Okay, function of one variable, yeah?
Yeah, this is a function of M and G. So G, you can fix M. Of course, you have to, this is going to...
No, psi itself, it's Fermi.
So psi is the Fermi field, okay? It's
one special variable.
What meaning?
No, it's just, I don't understand.
This is a Hamiltonian density. Okay, so if you integrate over this is a field.
This is what, 2-dimensional?
No, this is any dimension. Okay. Then this is a Hamiltonian density. You integrate it over the space, whatever it is, and you get the energy. Okay. Now I'm going to focus later on one spatial dimension, but this is in principle general. Okay. And again, this expansion is generic for any dimension. Now, if you change dimension, you will have to change the type of integrals you do, but the Feynman diagram structure is the same for any dimension.
Sorry, Marcus, just to discuss. Fermionic field depends on what?
The fermionic field depends on the language you're using. You're using the grand canonical ensemble, then this depends on the spatial directions, and then on the tau, on the Euclidean time direction, which is related to the temperature and so on. And okay.
And the sum is over spins.
The sum here is over spins. Here already the spins are already fixed. Here this is in a sense a standard Hamiltonian formula for fermions spin half.
You do have 3 up and 1 down.
Okay, sorry, this is a misprint. You have this should be down. Okay. Now this is really a standard textbook thing, apart from my misprint, which is also standard in some textbooks. Now, if you have a superconductor, many condensed matter theories will tell you that actually summing these Feynman diagrams is not a good point of view. What they will tell you is that you have to use the point of view of BCS theory, and they will tell you that the ground state is not really a perturbed free Fermi system, but really a condensate of Cooper pairs. And they will actually write for you a nice formula for the energy of the system, which is essentially going to be the free energy part minus delta square. And delta, a weak coupling, when G is very small. And delta is exponentially small, it's an exponentially small effect, and is what is called the superconducting energy gap. And this is the binding energy of a Cooper pair. So what happens is that fermions with opposite spin pair together, and they form some sort of condensate. And if you want to excite the system, what you have to do is to break these Cooper pairs, have less energy than independent fermions. Then you want to excite the system, you have to break one Cooper pair. And this is the energy of one single Cooper pair, so you break one Cooper pair, you excite the system from the ground state to the excited state. So you see the energy has this dependence on delta square, and if you just want to excite the system, you just have a gap of delta. So delta is actually the energy gap between the ground state and the first excited state. Now, one modern point of view of BCS theory of this point of view is that what you are doing is really a large n approximation to the system. So you could imagine that you have n flavors of fermions, so you have an additional index for the fermions. And then when you do this analysis of the theory at large n, the path integral has 2 different saddle points. You have the standard free system in which the fermions are free, and then you have a more stable state in which the fermions have the energy E free minus this exponentially small non-analytic term in G. So this is what people sometimes talk about the Cooper instability, because this condensed state is supposed to be more stable than the standard state. Now, this is not an analysis based on ordinary perturbation theory. This is not the analysis that you would get based on Feynman diagrams. This is a different point of view which you can interpret as a large n point of view. And one question that I would like to address as well is how this instability is actually reflected in ordinary perturbation theory. Now, in a sense, the energy gap, this quantity here, sets the non-perturbative scale of the theory. So this is a very important quantity of the system. So you would expect that anything which is exponentially small in G is going to depend on this energy gap. So I'm going to state for you 2 conjectures that I will try to illustrate later. So let me give you the conjectures here. Now the conjecture is that, the first conjecture is that the perturbative series of the ground state, the one that you can compute with the standard Feynman diagrams, forget about BCS theory, just start computing diagrams, the perturbative series of the ground state energy of a superconductor is factorially divergent and non-Borel summable. That's my first conjecture. And the second conjecture is that the first singularity in the Borel plane for this non-Borel series is determined precisely by the energy gap. So the energy gap sets the scale for the first Borel singularity. And let me tell you that this might look trivial, must look simple. I mean, you have a non-perturbative scale, which is this energy gap, and then this should be the non-perturbative scale in the problem, and then it should also determine the position of the Borel singularity. But people have not always been of this advice. People, for example, have thought for a long time that in theories with fermions, you wouldn't even have factorial growth in the perturbative series, because fermions, when you have fermions, things can have plus or minus signs, and there will be cancellations that will make the growth of perturbative series smaller than factorial. Okay, so there have been previous works arguing that that you don't have such a factorial growth. So my statement is that yes, you do have a factorial growth, and moreover, this factorial growth is not related to a semi-classical configuration, and this is related to the talk by Mithat, but it's more like a Renormalon type of singularity. So we will have. So what I claim here is that the superconductor energy gap is like a Renormalon, an infrared Renormalon for this many-body system. Okay. So, so these are the conjectures. I could give you, I can give you an additional argument maybe at the end of the talk. But when you have a conjecture like this, what is good is to have a simple model where you can do explicit calculations and eventually test the conjecture. So what is the simple model of a superconductor that you have in the market? Well, this is probably not the simplest model, but it's one of the most beautiful models. It's called the Godin-Jam model. So Godin was working in Saclay, if I understand correctly. So this is also like a product of this south area of Paris. This is a one-dimensional spin-half fermion with a delta function interaction. So it's the one-dimensional case of the Hamiltonian density that I showed you at the very beginning. Now, this model was introduced and solved in 1967, and it's a close cousin of another famous model in condensed matter, which is the Lieb-Liniger model, which describes not fermions, but bosons also interacting with a delta function interaction. And why these models are interesting to study? Well, if you want analytic control, it's good to have models which can be solved exactly, and both models can be solved exactly with the Bethe-Ansatz equations. So how do I do? Let me just summarize very quickly for you how these Bethe-Ansatz equations look like. Now, the effective coupling of the model is the dimensionless coupling, is the coupling constant G, and now in one dimension. And you have to divide by the density of particles. I will work all the time in the thermodynamic limit. The number of particles is infinite. The dimension, the volume or the length of the one-dimensional space is infinite, but the quotient is finite and fixed to be n. Then there is an integral equation which describes the density of Bethe roots. You don't know what is a Bethe root, think about fx as a sort of auxiliary function which gives the result for the problem. It's a very simple integral equation with a very simple kernel. There is a parameter b here which appears in this integral equation, and from the solution of this integral equation for a given b, you can find decoupling. 1 over gamma is the integral of this function over b. So if you want, this is a relation which gives this relation gives you the way in which b is related to the effective coupling constant, and then by integrating the second moment of this distribution, you get actually the ground state energy divided by nq, which is again the dimensionless quantity. So this is really a complete solution of the problem, in the sense that if you just solve these two equations numerically, for example, here is the solution. For example, this is gamma, and this is the energy. Here, when gamma is 0, you get pi squared over 12, which is the density energy of a free system of fermions in one dimension. And then as the interaction increases, you can see the energy becomes negative, and this is the energy. This is just the solution of this integral equation. You can do it numerically. Now, you say, well, you have solved the problem. What's the point? Well, the point is that this is just a number. This integral equation cannot be solved analytically. This is just a number that you get. And what you can now try to do is, as Ricardo was mentioning this morning, you can try to do a semi-classical decoding of this quantity. So can we write this quantity as some generalized Borel-Écalle resummation of a transeries? This is the first question that you have to do. And when you want to write a transeries, the first thing you have to do is to find the perturbative series, just the perturbative expansion in gamma. Of course, we could do this with finite diagrams, but the next question you should ask is, can I extract from these sets of integral equations the perturbative expansion of the problem? Now, before doing this, let me remind you that the physics of this Godin-Jam model is actually the physics of a superconductor. The ground state of this model is a BCS-like state made out of Cooper pairs, and you can compute the energy gap, an important calculation you can do, and it's exponentially small in the effective coupling constant with a very precise weight. And you can see from the Bethe-Ansatz equations that fermions here actually pair up, Furon Cooper pairs. You have a given number of spin-up fermions and spin-down fermions, they will pair up. And if the number of spin-up fermions and spin-down fermions is different, there will be some isolated fermions that they cannot couple to. But the absolute ground state of the system occurs when there is equal number of spin-up fermions and equal number of spin-down fermions, and all of them are paired up, forming Cooper pairs. And this is the case I will consider. This is the case what is called zero polarization, equal number of spin-up and spin-down fermions. Everybody is in a Cooper pair. So this is really a toy model for a superconductor in one dimension. It's not such a toy model because people are actually striving to implement experimentally these systems, and they are quite close to do it. They have not done it yet. So let's come back to this question of extracting the perturbative series from the Bethe ansatz. Now it turns out that this is a very difficult problem. And if you read the paper of Lieb-Liniger, which is the paper which essentially introduced the Bethe ansatz in condensed matter systems, you find that extracting the perturbative system was something that they could not do. And this is just because zero coupling is a singular limit of this Godin's integral equation. So it's a problem that you find both in this Godin-Young model and in the Lieb-Liniger's model. Now, after 50 years, there are only the first two coefficients of this series are known analytically. And this was done work by Ida and Guadati. Tracy and Whedon wrote various papers in the last 4 years trying to do this. As I said, it's the same problem in the Lieb-Liniger model. So the first thing you have to do, if you want to do resurgence, is try to extract the perturbative series from this Bethe ansatz. And it turns out that you can actually solve this problem. There is a very nice old paper by Popov, the same one of Fadeyev Popov, where he actually already found the right strategy to do based on previous works by mathematicians. And there was a very nice technical breakthrough by Dmitry Volin in 2009 in the context of ADS-CFT that you can adapt to this problem.
Sorry, just
yes.
In principle, I can take this as a one-dimensional integrable system.
Yes.
So, because your rules precisely come from the corresponding Bethe equation.
Yes.
And the question is, can I address this question from the quantum spectral curve formalism like Dima did?
Well, I don't know if you can do it from the quantum spectral curve. I mean, the question is you want to extract this perturbative series, and that's the problem you want to solve. The strategy that I'm going to show you is not based on the quantum spectral curve. It's slightly different. Maybe it turns out to be the same thing, but I don't know any other way of doing this. Okay? And as you see, it's not I mean, people, people have even done numerical fitting of these coefficients. The kind of things that Ricardo was showing today. You compute a lot of numbers, and then you try to fit this to the coefficient. You try to compute these coefficients numerical, and you try to fit into exact expressions. So let me give you a very short summary. This is, in a sense, the kind of technical, the technical kernel of our method was actually to solve this problem. So the strategy is very simple. You write two answers for the integral equation. The integral equation describes a density of roots. Okay, so it's a function like this, and it ends up in b and minus b. And then you write two answers for this solution. One is around the origin, another is around the boundary, and you're trying to match these things. This is an old idea which goes back to the work of Hudson in the 50s. Popov rediscovered this idea in the 70s. But doing this doesn't take you very far. With a lot of work, you can get two coefficients. This is what people did until very recently. Now, there is a key improvement, which is based on an idea of Ivan Kostov, Servan, and Volin, again, Saclay work, and Dmitry Volin, is to use the resolvent of this density. So this is the function that you want to solve. And it turns out that it's much better to use the resolvent of this function, which is defined in this way. Now, once you find this resolvent, it turns out that the inverse Laplace transform of this resolvent near the boundary and in the limit of infinite b can be obtained in closed form. And this is, in a sense, the key ingredient that was missing. And this Laplace transform has a very closed form, which is this form here. And this function encodes all the information of the perturbative series in a kind of very convoluted way. You have now to extract it from this function, but this function, which is as I said, the inverse Laplace transform of this resolvent near the boundary and in the limit of infinite b, has all the information. It looks like one of these anarchist functions that we were seeing this morning, but I don't know if...
This is Stirling formula,
yeah? Eh?
This is Stirling formula, yeah?
Yeah. This is gamma of S, yeah. But as you will see, it has a lot of information in it. Now, once you do this fitting, you can actually write the perturbative series. And we were able to break this bottleneck of 2 coefficients, and now we can essentially calculate any number of coefficients if we have enough computer power. We have computed 35 coefficients, but we are now getting 40 or whatever. So you see that this is the energy of the free theory. Then you have these 2 contributions that were computed, were known. And then, starting with the cubic order, you have the zeta functions evaluated as odd numbers. They do not even occur linearly. You can have products and squares and so on. And this is the answer. Okay? This is the answer for the perturbative series. And we have these first coefficients can be also checked with Feynman diagram techniques. You can actually do the Feynman diagram technique and check that you actually get this number. So this is the exact formal power series for the perturbative energy in the ground state, obtained from the Bethe ansatz. But as I said, this agrees to all the orders we know with Feynman diagram calculation, and we expect this is the right answer. Okay, so now, if you want to do resurgence for this, in a sense, the easier way to work, the easiest way to go is to actually look at the large order behavior of this series. How does it diverge this series? So you can do a numerical study of this series. So let me define this coefficient Ck, and then you can see numerically very easily that, first of all, they diverge factorially. So these cancellations in fermion systems is not actually taking place. There is no cancellation between different contributions. And actually, you can see that the divergence is controlled by this pi square. So you can see numerically, after doing some Richardson extrapolation, that this quotient actually converges to pi square very fast. And you can actually guess that the non-perturbative, you can actually deduce from this latter behavior that the non-perturbative ambiguity that we have here is precisely of this form, e to the minus pi square over gamma. And this is exactly twice the value of the energy gap, of the superconducting energy gap. So this has the exponential dependence of the square energy gap in agreement with the conjecture we were making. Now the fact that the energy gap appears square, I don't have a full justification for it, but you can see that in BCS theory, the correction to the energy involves delta square, not just delta. So this is in sort of heuristic agreement with this. Now, of course, this is a non-trivial test. As I said, we have to generate all the series. And it's also good to have other models. But we actually did another test of this conjecture in the Hubbard model. The Hubbard model is a sort of discretized version of this model on a lattice. And it has essentially qualitatively the same properties. And you can study this model at half filling, where the ground state energy series can be calculated analytically. So you have a closed formula expression for this coefficient Ck, and you can check again that the large order behavior of this series is exactly governed by the superconducting energy gap. So, from the point of view of resurgence, this means that, remember that this thing can be computed. I mean, this is a number. When you solve the integral equation, you get a number here. This number has to be decoded as a transeries. The first part of this transeries is the perturbative series that I just showed you. And then they should be exponentially small terms of this type. This is, in a sense, the simplest answer you can get. And actually, from the numerical resource we have, this coefficient C1 is there just to cancel the imaginary part of the lateral Borel resummations. You can think about this as a Stokes constant, and its value is plus minus I from our numerical results. So it's just purely imaginary. Now, when you look at a perturbative series in a quantum theory and you find that the large order behavior is controlled by this Borel singularity, the first question you have to ask is, what is the physical meaning of this singularity? What is this singularity representing? What are the sources of Borel singularities in a quantum theory? Well, essentially, as far as I know, there are 2 essential sources for this. And this recaps a little bit the discussion that Mitat did in his previous talk. The first sources are instantons. Now, one way of that series can diverge factorial is that because at each order, the total number of Feynman diagrams contributing at each order grows factorially. But each diagram has only exponentially growing growth. So exponentially only grows exponentially. So, for example, if you go to this perturbative series that I was showing you here, you can see that this is order 1, this is order 2. So at order n, the number of Feynman diagrams will increase factorially, and this factorial source of growth of the series is what is supposed to be encoded by instantons, by semi-classical configurations of the path integral.
So it's no ultraviolet renormalization.
No, here everything is finite. You don't have to do renormalization. And this is also interesting regarding what I'm going to do. So this source of factorial growth has a semi-classical interpretation. Now, another source of factorial growth in quantum theory are precisely these renormalons that Mitad was mentioning. So what are the renormalons? Renormalons are special types of diagrams that after you integrate over the Feynman momenta in the Feynman integral will lead to factorial growth. So it's not the number of diagrams that is increasing, but at a given order there is a very bad diagram that is giving you this factorial growth when you integrate over momentum. I'm going to give you some examples, and in general, so you take a random theory, they do not have a semi-classical description. Also, there is the work of Mita, Gerald, and other people who have found such semi-classical descriptions in many models after this adiabatic compactification. And I have to say that one of the motivations for this work was to try to find scenarios where these ideas of theirs could be tested maybe in a simpler way. So maybe this is going to provide a simpler example of this behavior. Now, renormalon diagrams are absent in many theories. For example, in quantum mechanics or in Chern-Simons theory, there are no renormalon diagrams. Now, in the presence of renormalon diagrams, as Mitad was explaining, instanton effects might become secondary. They give you singularities in the Borel plane, but are very far from the origin, and then renormalon singularities are going to be more important than instanton singularities. And this is believed to be the case in QCD, for example. Now, if you do a pure diagrammatic analysis, it's very hard to know exactly where is the location of the Borel singularity. Okay? Now, typically what you do is you try to argue that some classes of diagrams are going to dominate. They are going to be more important than instantons. And in renormalizable theories, you can use additional tools like renormalization group, operator product expansions to locate the singularities. Okay? But in general, if you find that there are special diagrams that lead to factorial divergence after integration over momenta, you can suspect that these are going to be the responsible persons for the singularity that you are obtaining. So what happens in the case of superconductors? What happens in the case of this Godin-Young model? Now, it has been pointed out sometimes, although this is not universally acknowledged from what I have seen in the condensed matter literature, that there is a special type of diagrams in Fermi system which give you this divergence. So these are called ladder diagrams. So these are diagrams which are circular like this, and they have ladders. They can have as many ladders as you want. And you can see that at every given order, there is only one single diagram like this. But this diagram, once you integrate over momenta, is going to diverge factorially. And these, by the way, are also the diagrams that people use to exhibit the Cooper instability. You can use these diagrams to argue that there is some pole in the, in the 2-point function or in the 4-point function, and this pole should be interpreted as a bounded state of resonance and so on. Now, on the other hand, if you use instanton estimates for the Godin-Young model, as I said, you don't even expect full factorial growth. So there are grounds to believe that this Borel singularity that you observe clearly in the Godin-Young model is of a renormalon type, is due to some diagrams which are divergent too fast. And we have identified actually two classes of diagrams with factorial growth. Ones are ladder diagrams, the ones that I was showing here. You can actually consider a subset of these diagrams, which are the ones that are called with one pair of whole lines. This is a technicality. If you are not familiar with quantum many-body theory, this is okay. I was not familiar myself with these things 6 months ago. So you can actually compute the growth of these diagrams, and they grow factorially with a factor 2 pi square minus k. So this is twice the singularity that we found. But it turns out that in one dimension, you have another class of diagrams that also diverge factorially. And this is actually has not been really appreciated in the condensed matter literature, that on top of ladder diagrams, in one dimension, also the standard ring diagrams also diverge factorially. Ring diagrams are very important in condensed matter because these are the diagrams that, for example, people use to actually calculate the energy of a system of interacting electrons. There is this famous Gell-Mann-Bruckner formula which gives you the contribution of these ring diagrams to the energy of a gas of electrons and so on. It turns out that in one dimension, ring diagrams grow factorially and precisely with the growth that we have observed in the empirically in the total answer. Okay, so I think this gives a strong indication. This is not a proof, but this is a strong indication that these diagrams, these divergent diagrams, are the ones which are responsible for the Borel singularity that you observe in the total energy. Now, it's very interesting if you compare this to standard renormalus. Now, renormalus, there are infrared renormalus, as Mita was mentioning, but there are also ultraviolet renormalus. And they are called ultraviolet or infrared renormalus because the divergence, the factorial growth that they give, come from the region of very large momentum or very small momentum. Here, the dangerous region is not the momenta very large or the momenta very small, but are the momenta who are close to the Fermi surface of the Fermi system. So when the momenta of these pairs of these Cooper pairs are close to the Fermi surface, then you have a logarithmic singularity in the integrand from these Feynman integrals, and you have this factorial growth. So I guess this gives a strong indication that these renormal type of diagrams are actually responsible for this singularity. And actually, analyzing these diagrams is easy in higher dimensions. For example, in 3 dimensions, you can consider now an actual superconducting system, the kind of superconducting system that people observe, for example, in gas of cold atoms and so on. Those are these systems in 3 dimensions, which are described by the same Hamiltonian density. And then, of course, you don't have a Bethe answer that allows you to extract the exact perturbative series. But you can analyze ladder diagrams and see how they diverge. And what you find is that the singularity that you find, these ladder diagrams diverge factorially, and they lead to a Borel singularity, which is twice what is expected from our conjecture. But as I said, this is a restricted type of diagram. So it could happen in 3 dimensions. This conjecture is not yet settled, but it could happen that if you add more diagrams, you could actually enhance the singularity to what it should be. So the analysis of diagrams is not conclusive, but it gives you strong suspicions that first, the singularity is not semi-classical, and second, that it really comes from some families of diagrams. I mean, unfortunately, here we don't have these additional tools yet, like in quantum field theory, to locate this singularity more precisely. Yes?
You mean like, if I consider this 3-dimensional model, there might be contributions from non-ladder or other type diagrams?
Well, the problem is that the ladder diagrams... Yeah, absolutely. No, your question is very good. The question is that when I consider these ladder diagrams, I only consider technically what are called ladder diagrams, one pair of whole lines. So these are not even all the possible ladder diagrams. So if you consider all ladder diagrams with more than one pair of whole lines, yeah, so it's a restricted set of ladder diagrams, absolutely. Yeah, sorry for the imprecision. It's a restricted set of ladder diagrams. But also, we know that ladder diagrams diverge factorially, but it's not, I don't think anybody knows for sure that there are no other diagrams that can diverge factorially. Okay? We know, for example, that ring diagrams in 3 dimensions do not diverge factorially. They only grow exponentially. But who knows what is there, right? I mean, this is a space of many, many diagrams. It could have something, there could be other dangerous diagrams. Okay? And now, I think in the worst of the cases, if this is not enhanced, this just means that our conjecture has to be slightly changed in 3 dimensions to allow for a multiple of the singularity. Notice that these are integer multiples of the singularity that I'm telling you. I mean, this is a multiple, this is twice the singularity that our conjecture predicts, this restricted set of ladder diagrams. So it's not so far off. Huh? Okay, now let me mention another model. This is not a superconductor, but is very similar to what I have been discussing, which is now the model of bosons, the Lieb-Liniger model. Now, with the same techniques, you can analyze now this model, which is one of the most important models. This model can be implemented in the laboratory. This is really a model where people actually compare almost in a routine way experiment to theory. And it can describe bosons with positive delta function interaction and can be solved with the Bethe answers. Now, the integral equation that appears in this model is exactly the same one as the Godin's equation, but with a different sign here. Instead of a plus, you have a minus. And you can solve with the similar techniques. Now, you can actually also compute the inverse Laplace transform of this resolvent, and you will find this function here. So you see it's very similar to what I had before. Instead of having a 1/2, you have a 1. And again, this encodes the full solution to the problem. Okay? So you can use all this information to actually calculate the perturbative expansion of the energy. And this transparency is especially dedicated to Jan, who studied the capacitor, the problem of the... So the same integral equation appears in the old problem of calculating the capacity of a circular plate condenser at a small separation. So this is a problem in electrostatics that maybe you have been tortured with this problem when you were a student in physics. And Jan, actually, when I was working on this project, I discovered that Jan had written many papers on this. You forgot about them, but you know, but the web keeps everything. So, one of the things that Jan was studying was the formula, you know, how to calculate the asymptotic expansion of this capacitor. And again, only these terms were known in the literature. Okay, this is everything that people knew before. We developed this method, and now you can actually compute many of these terms. And I think Jan was relating this to invariance in Riemannian geometry, right? Now you can actually compute all these numbers. You see it involves zeta functions as well, and so on. Okay, so this is in a sense a bonus of this project. Okay. Now coming back to the perturbative series of the ground state energy of this linear model, you find this series. So these first two terms you can compute them very easily using Bogoliubov's theory of interacting bosons. And again, you have all these coefficients here. You notice that there are fractional coefficients. This is the typical signature that you have a condensed state of bosons. The series is again factorially divergent, is non-Borel summable, and you can also deduce the larger the behavior. Numerically, you find that with high probability, this is 8 pi. And this is a little bit what happened with this Bender-Boo calculation. You know, Bender and Boo were studying the quartic oscillator, and they just computed many coefficients of the perturbative series, and they found a number that they identify by numerical fitting. So this is what a little bit what we are doing here, but we don't really know what is this number. Now you can ask now the same question: what is this number giving you? I mean, every time you have a Borel singularity in a quantum theory, there should be something behind. There should be some phenomenon, some instanton, some renormalum behind. Now for the Liebling-Niger model, I don't really know what is this 8 pi. We know that this would correspond to a transeries which would have a exponentially dependence of the form e to the minus 8 pi over gamma 1 to the 1/2. And what I suspect, but this is something that I would like to make sure in the future, is that this is really due to an instanton. And this is an instanton that nobody has studied. It should be the instanton of a non-relativistic 2D field theory describing the Liebling-Niger model. The Liebling-Niger model in terms of quantum field theory is a two-dimensional quantum field theory for a complex scalar field with a non-relativistic kinetic term and with a phi-4 interaction. And if this phenomenon is related to an instanton of this theory, you should be able to find a finite action solution of this of the Euclidean equations of motion of this action principle that should reproduce this 8 pi. So I think this is really very interesting because the Liebling-Niger model is an experimental model. So this could be a prediction of resurgence for something that you might eventually see someday in the lab. I mean, and this really, nobody knows about this. I talked to the expert, one of the world experts on one-dimensional condensed matter systems in the world, who happens to be in my department, and he doesn't know what kind of effect could be exponentially small in the Liebling-Niger model. But Resurgence tells you that such an effect should exist, because this is what is controlling the larger behavior of this perturbative series. It's there. So what is this? And maybe there is something interesting here.
Sorry, Marcus.
Yes.
There is no way to relate this to the BCS. I mean, because the principal Cooper pair is also, I can represent as a boson. I mean, at the end of
yeah. No, I understand what you mean. There is even this idea that you can, in a sense, interpolate between the superconducting state and the condensed state. Yeah. This could be the case, but when you do this, this is something that people have. This is called the BCS-BEC crossover, the crossover between BCS superconductivity and Bose-Einstein condensation. But still, when you do this, you essentially glue the Godin-Young model to a Liebling-Niger model. This has been studied, but still, this doesn't have the dependence of. That you would, I mean, it's not the same kind of effect that you have.
This was I can extract this from the ladder construction. I mean, such factors.
Well, the problem is that the perturbative series here gets completely reorganized. I mean, the perturbative series for this model, the bosonic perturbative series is very different from the fermionic perturbative series, precisely because you have a condensate. So you have to do perturbative series in the presence of a condensate, and you don't. I mean, the diagrams get completely reorganized, even if you think that this is a continuation of the Godanian model. I think I would say that the most straightforward possibility is that there is a finite action solution of this model.
Pretty sure about that. I don't have any extra or special saddle points like in previous case, so that I would say my renormalants are dominator or instant on contribution.
Well, it could be that there are renormalants in this model, okay. But you see, there is a difference between fermionic systems and bosonic systems. In fermionic systems, instantons, you don't even expect that they give you factorial behavior. Here, instantons could give you factorial behavior. So maybe we can try first to see if there are some instanton solutions. I mean, after all, we know, for example, that let me actually tell you something else. We know that the relativistic version of this theory has not finite action instantons, but almost finite action instantons. It's the famous vortex that people like Polyakov studied. So it's not so. It wouldn't be. But of course, it could happen, as you say, that there are no instantons that lead to this, and then one should look again to some sort of renormalon diagrams that are responsible for this. Okay? We know, for example, that in a two-dimensional field theories, this is a non-relativistic two-dimensional field theory. In relativistic two-dimensional field theories with phi-4 behavior, like the ones that were studied recently by Marco Ceroni and collaborators, again, instantons are really the responsible for large order behavior. So I would say, based on this, that this is the first place where I would look at. But as you are saying, maybe these are renormalons again. Okay. But I think it's very interesting that Resurgence is telling us about an effect that we didn't know about in a very central model to condensed matter theory. Okay, let me already reach my conclusions. But I think the main idea is that quantum many-body theory is a very important arena where resurgence ideas could and maybe should be applied. I'm not a moralistic person, so I wouldn't say should be applied, but can be applied, and it's a pleasure to apply them, and it's a very interesting new place where you can think about resurgence. And as I said, the larger the behavior of this, the main technical point of our work was to actually generate this perturbative series. Already using resurgence to this series, you see interesting new insights on non-perturbative physics. For example, the Cooper instability, nobody has understood this instability as a singularity in the Borel plane. I mean, this is just because in condensed matter it's very hard to generate this perturbative series. So I think this gives really a new perspective on the Cooper instability. So this energy gap, which is one of the most non-perturbative effects in quantum physics, now you can really understand it as an exponentially small correction in a trans-series. And it controls. This is also an open question. I mean, if you read all these papers on larger, there is very few results on larger behavior in condensed matter theory. Very few results. And if you read all these papers, there's not even a hint of what is the object driving the larger the behavior of the perturbative series in many fermion systems. Although when you look at this, the answer is obvious. Is the Cooper instability? Is the exponentially small non-perturbative effect discovery in BCS theory? This is the effect which is controlling the larger the behavior, probably generically, in any weakly interacting Fermi system. And it's also very interesting that when you start looking at the physics behind this, you just find very similar physics to renormalon physics. And I think this was also not really pointed out in the literature in a clear way. So, of course, when you see these things, you start seeing many things which are similar. You see that in both cases there is something like a Landau pole and so on. But it's really something that you can see very clearly. I mean, the physics of this superconducting energy gap, as it manifests in the larger behavior of the perturbative series, is a renormalon problem. It's a renormalon phenomenon. It's the same one. It's surprising that people have not realized this before. Now, in the Liebling-Niger model, the large order analysis also unveils this new non-perturbative effect, which I think should be understood better. And I think there is a very interesting possibility of finding new physics there, in a sense. Now, from the point of view of mathematics, I think this opens also a very interesting area where we should use our resurgence tools. Because, again, this idea of semi-classical decoding is that it's not enough to have a good numeric or good explicit solution. I mean, having this Bethe-Ansatz solution, in a sense, doesn't tell you much about what is going on, right? I mean, as Wigner said once, you know, it's good to know that the computer understands the problem, but I would also like to understand the problem, right? So, you know, Resurgence is a way to understand these numbers that your computer spits off, you know, in a more conceptual way. So what is, I think, is a very interesting arena of research is to take all these Bethe-Ansatz solutions, all these exact solutions in terms of the Bethe-Ansatz, and try to extract the trans series which is behind, which has to be there. I mean, you take this the Godanian model, there is this perturbative series, the perturbative series is non-Borel summable, there is a Borel singularity in the positive real axis, so for sure there has to be something exponentially small that has to cure this, such that by doing lateral Borel resummation you recover the exact answer. That has to be the case. So how could you compute such a trans series? I mean, it's not a simple problem because we have a lot of trouble just to compute the perturbative series. Now, computing analytically these exponentially small corrections from the Bethe-Ansatz, I don't think is going to be very easy, but I think it's a very interesting question. And I think, again, coming back to these ideas of Mittat and Gerald, I think also these Fermi systems give you, in a sense, a surprising realization of renormalon physics, which has all the ingredients of renormalons, I mean, factorial divergent diagrams and so on, but in a sense, in a much simpler setting. As Maxime was saying, here you don't have to worry about renormalization in the standard sense of regulating. I mean, all diagrams are finite. At least more precisely, at a given order, the sum of all diagrams can be trivially regulated in such a way that they are finite. But you don't have to use an explicit RG group or anything, a renormalization group or anything. So, in a sense, this is maybe an opportunity to understand the renormalon effects in a nice way. And we also know that these renormalon effects, the exponentially small contributions which correspond to these diagrams are also in the Bethe-Ansatz equations. So in a sense, the Bethe-Ansatz equations is telling you how you should solve the renormalon problem in these theories. So again, I think this opens a very interesting door to understand these problems. And thank you very much for your attention.
Questions and remarks? Okay.
What happens to the ladder diagrams in 2D?
Oh, they also diverge factorially. Yeah, they also diverge factorially. That's a very interesting case.
And the singularity?
The singularity you can actually compute it numerically. It involves a 3 somewhere, something like 3 pi or something like that. So, but I haven't looked yet at it because in 2D, the way that in 2D the delta interaction potential, you have to renormalize it, and then it's a little bit more subtle to understand, you know, the relation to the coupling and so on. But this is something that we plan to do. So it's clear that ring diagrams do not diverge factorially, so you have to look at the diagrams. But this is one of the things that we are really planning to do.
But there's no clear relation to a Fermi surface approach.
No. The renormalon singularity is also related to is due to a singularity near the Fermi surface as well. Yeah, I think so. Yeah.
Yes. Question. In the very beginning, we have the series, and besides the first two terms, the rest will be polynomials in odd zetas. Yeah.
Yes.
Yeah. In fact, I heard something similar in XXY models. Somebody told me.
Sure. It might be the case because these are some models solved with the Bethe-Ansatz. So I don't know if you can extract. I don't know if these techniques have been applied to these models, but of course there is a Bethe-Ansatz underlying. Of course, the appearance of this zeta 3 and zeta 5 is
no. The miracles are not no multiple zetas at all. So it's only polynomials. It's odd zetas.
Right. Yeah.
You don't have any explanation.
No, I don't have any number theory explanation. Actually, people thought at the very beginning that it was linear in the thetas, so there were no polynomial structures, they were just linear. But actually, the first ones are linear, but you see that already at order 5 or 6, you have products. So, yeah, I don't have any clue about this. But these are analytic results, I mean, because people have derived some of these coefficients by numerical fitting. These are really analytic. I mean, yes?
In fact, worked on some model where you can have renormalent from the Schwinger-Dyson equation. Could you say that you could use something like a self-consistent equation where you plug a modified propagator in your...
Yeah. No, I see what you mean. Yeah. No, people, that's a very interesting question as well, is that in some cases, you can resum the ladder diagrams. And in a sense, you hide this renormal on singularity. You can do that, for example, in 3 dimensions. In 3 dimensions, you can actually resum partially at least some of these ladder diagrams, redefine your vertex in such a way that includes these ladders, and then you do perturbation theory with some sort of renormalized vertex, and then the degree of divergence changes when you do this, okay? Because you have resum some partial diagrams. But it's not always the case that you can do this, because actually doing this is in a sense a partial resumation, a partial prescription for resuming this divergence series. For example, in 1 dimension, you cannot do this. You cannot do the same trick as in 3 dimensions for resuming these diagrams. You try to do it, you find a divergence, you have to regulate in some way. So it's just that you are lucky that in 3 dimensions, at least these one whole pair ladder diagrams, you can resum them in a naive way. And then people use this in perturbation theory. Yes, that's true. But this is not universally possible. Huh? Already in 1 dimension, it fails.
Looks like resurgence is very useful in those kind of physical systems in which there are phase transitions, and looks like this can be applied to many statistical systems. So is this correct, or is there something particular in superconductivity that allowed you to start applying resurgence to low energy physics? And if not, if there is nothing particular, why did you choose superconductivity to start with?
I didn't choose. I mean, I just of course, this is the context of discovery and the context of justification. I didn't discover this in a sense by saying I want to understand superconductors. I mean, I can't tell you why I happened to stumble on superconductors, but it was not because I said, let me look at superconductors. I was interested in renormalons. I wanted to understand renormalon physics in these models in some precise way, and eventually ended up there. Now, in terms of phase transitions, everything I did here is at 0 temperature. Now, I think a very interesting question is the following. Now, study the system at finite temperature. It's clear that at some point, the energy gap will vanish, because this is what a superconductor is. As you start heating the superconductor, this energy gap vanishes and the system is no longer a superconductor. So, if you do perturbation theory at finite temperature, would you find a similar situation? I mean, would you find that as you hit the system, the Borel singularity starts moving away in the real axis and then disappears to infinity precisely at the transition temperature? That is a very interesting question. And this is how you would understand the phase transition, the superconductor phase transition at finite temperature as in terms of resurgence. Now, that's very interesting because we know that at finite temperature, the perturbative series is going to change. But precisely because there is such a phase transition, it will be very interesting to kind of monitor the location of the singularity. But here, everything is 0 temperature. Okay. Yes?
You had 2 non-perturbative vectors. One of them, can you write them, can you show me again?
Yes, what you mean?
One of them was coming from the gap, and the other one is 8 pi divided.
Yes, absolutely. So this is the effect for Godin-Yang. Okay.
It's very interesting because in some circumstances, you see one of them is controlled by 1 over gamma.
Yes.
The other one is controlled by 1 over gamma to 1/2.
Absolutely. Yeah.
So there are some circumstances in which this gamma to 1/2 comes about as an instanton in the effective field theory.
Yes. Yes.
So it just reminds me that I just want to comment on that. So, for example, even if take Yang-Mills, there are usual instantons, but
yes.
if you put it on torus,
yes.
If you look to tunnelings related to center symmetry, okay, minimum. This is the work of Lucher and Ball and others. You can show that the tunneling is exponential minus 1 over g, not g squared.
Oh, I see.
And that comes about because of this is really an instanton of the quantum action, strictly speaking.
I see. That's interesting comment. As I said, my first guess would be that this 1/2 would be related to a finite action configuration of this bosonic theory. but I don't really know. I don't have anything concrete to say on this.
Questions, and thanks to the speaker again.